So make sure you refresh the webpage. I changed a few things. So the old assignments, the assignment links have been linking to one from last semester. I had the links broken. Most of them now should be linking to a PDF file that's not there. That's because they haven't been posted yet. So I'll probably post the first one either tonight or tomorrow, so the TAs will look it over just to make sure everything, just double check to make sure everything makes sense. So this is the first assignment will mainly actually be about the lecture last Monday. There'll be a few things today. So as soon as it's posted, I'll post a link. I'll post something in the discussion group. An announcement once it's posted. Then you should be able to start working on it. You'll have roughly 2 weeks to do it. So I'm guessing that should be more than way more than enough time. But so I'm asking you, or I'm suggesting you try doing the assignments in LaTeX. I'm guessing there'll be some hiccups and how to turn them in if you haven't turned stuff in on Canvas before, or you haven't used LaTeX before. It's not required to use it, but for certain writing and with mathematics and like some file that you can upload online, it's typically the preferred way to do it. And I have, if you forget, there's links right here where the mouse is that has some sample files. You get those compiled and you can just kind of modify those. There's lots of resources online for how to do LaTeX. So after the assignment's posted, feel free to ask any of the TA's questions around the discussion group. It's a great way to try and, if there are any questions on that. All right, so a few of you have also asked me about the projects. So it's, one of the hard parts is choosing a topic and maybe choosing it on a small team. I reckon, unless there are special circumstances, a couple of you have talked to me about, I want you to work in groups of 2 or 3. Actually, the amount of work you have to do is probably a little bit less if you're in a group. It's also less work for me. So that's probably why I'm encouraging it. But I think you can actually accomplish more interesting things. So some of the more interesting projects in the past years, they were by groups where they worked together really well and put together some really nice projects. So if you look, so the project PDF, it used to be linked to the one from last year. There have been some slight modifications, especially with the dates. The other thing is choosing a topic. If you haven't looked at this yet, I suggest you do that. The proposal is not due for still a few more weeks, but you should start thinking about this. Some people have asked me, that's great. Run ideas past me. So it may be tough to come up with a topic. If you're working in a research group, I recommend you use topics from your research group if you can. There'll be something you're already interested in. I don't want it to be the same thing you're doing for another class exactly, but if you can, or for your that you have for some other specific requirement, but if you can carve out some part of it that fits within this, that's great. If not pick some topic that you have a passion about. If you're interested in the topic, you're more likely to do more interesting stuff. So I'm hoping you pick something you're interested about. I'm pretty flexible on what the project is about. If you still don't have any idea, there are a number of links to some websites that have some interesting data sets. If you go to these links, you can browse through the data sets and try and find something that looks interesting. And you can then try and find some way to analyze it. The goal is to take something that you're going to be learning about in class and go much more in depth about it. And if you have trouble coming up with ideas or finding people to work on something with, post something to the discussion group, and that's a great way to kind of find people about a certain topic. the last thing I'll mention is one of the students from my class last year is now working as a data scientist in the Bay Area for some health information firm, and he said that there's some data sets with this company that he thought might be very good for a project for 2 or 3 people to work on. He didn't say exactly what it was about. It was about like customer logs on websites, but having to do with health medicine. If you're interested in that, contact me, and I'll select a few people as a group, and I can put you in contact with them and see if it's a good fit. So it'd be good to do that sooner than later, because someone else may also contact me about it, and you want to check this out first. I don't know much of detail about it, but it could be something for you. All right. So any other questions about the project right now? Okay. All right. So today we're doing kind of the last more abstract lecture on these kind of basic statistical principles, these basic randomized techniques, and then we'll start getting into some actual discussion about certain types of data and actual algorithms for looking at this data. Sorry, next week, keep in mind Monday is Martin Luther King Day, and there's no class on Monday. So you can show up on Monday, but no one will be here. All right. Okay, so what we're going to kind of continue a little bit about what we talked about on Monday, where we're going to have these n bins, and then we randomly put k balls in the bins. Okay, so you can think of the n bins as being this array. And then there's going to be some hash function, which is going to take some elements from some set, and it's going to map them randomly in here, and we're going to look at how many elements, distinct elements from the set we need until certain properties happen. And we looked at 2 properties. We looked at the first collision, and this happened about when k was about square root of 2n, and we looked at all bins non-empty, and this happens about when k is equal to n log n. Okay. So now the third property we're going to look at today is when all bins roughly are even. And so this will take this is not as concrete to define, so I'll need to spend a bit of time defining precisely what I mean by this. And then we'll look at this phenomenon. So there are kind of two key things that you should take away from this class. So the first one is kind of a fairly the first one is a fairly fundamental thing to keep in mind when dealing with data, and this will kind of illustrate this phenomenon. And the second one will be some particular forms of bounds on probability that will be really useful in thinking about how to bound the probability of these randomized algorithms. And I'll spell out these bounds and kind of they'll be a bit technical to write and to put on the board, but we'll kind of break down the parts and think through what they actually mean. And if we have time, we'll go through an example of how to use it for looking at specifically at a very So the first main principle is that often when you're doing data analysis, and this is not necessarily something you do at a very high level, but this will come up in some like low level inside several techniques is this kind of three-step process of trying to analyze the data. So the first step is to create a very simple a very simple estimate. So you're trying to estimate some property from some large data set. Find a way to create a very simple estimate of it. And this should be, and so this may be random. So if you're estimating something, you're not getting the right thing. You want random, but you want it with the right expected value. So you're going to get some estimate of something, but it's at the right expected value. Once you do this, then you can repeat this process several times. And then analyze the aggregate. Okay, so the kind of the key steps here are going to be somehow trying to figure out how to create a simple estimation of something. And this does not actually need to be that accurate, but it needs to have the right expected value. So this cannot be some sort of biased estimate. If you figure out how to do this and it's random, then you can repeat this with every time with different randomness. So these are not all correlated with each other. You want these to repeat this process several times. Make these preferably independent, but you can make them, they can be negatively dependent and everything works if you know what that means. And then you can analyze the aggregate. So we'll take all these estimates and we'll combine these together. And so kind of what we'll discuss today is a general technique for analyzing this aggregate. What does this mean as far as the probability goes? So this is a theme in some of this data analysis that we'll see several times. I guess in 2 weeks, the min hashing and LSH technique on the 27th and 29th will be kind of basically in this mold. We're going to create some simple, very simple estimate of something that seems like it's going to be way too simple. And we're going to combine a bunch of them together and get very accurate estimates of something. Okay. And then it'll show up later on in the classes. All right, so this is, I'll maybe try and touch back on this. But now let's try and look at this balls and bins problem again. Okay, so we're going to look at this balls and when all things are roughly equal. Okay, so I need to define what this means. So one way of thinking of this process is to create a random set, and we'll call this SK. And this will be the set of all the elements that we see. Every time we throw a ball in a random bin, it gets a value between 1 and n. Right, so this will be a set S1, S2, up to SK, where SI, SJ is, SI is going to be in n. Right? So each of these is going to be a number between 1 and n. Okay? And we're going to look at a value called the frequency. We'll call this Fi. is going to be it's going to be the size of the set such that S Fj or Si is equal to J. Okay, so if you're not familiar with this notation, when you put the curly brackets around something, this is they show a set. It's elements here that satisfy this condition. Right? So this particular element of the set, Si, is equal to the value J. And I put these bars around it. This is the cardinality. This is the size of the set. Right? So this is the frequency, the number of elements that have that have a value J. Okay? So now, I know if I do this k times, and there are n possible bins, then the expected value of Fj is going to be, right, so who's paying attention? What is the expected value of Fj going to be? I heard some mumbling. All right. Okay, who wants to, okay, so I'm taking any one of these bins. So let's say number 4 here. Right, so this is J equals to 4. And there are n different things. So let's say n is 100. There are 100 spots, and I'm going to throw in 300 balls. Okay? So how many balls do I expect to get into slot 4? 3. Good. So now if I wrote this in terms of k and n, what would this value be?
K over n.
So this would be k over n. All right, so the expected values, and this is the same if it was j equals 3 as well. It's the same answer. It's a uniform probability. A lot of this will, this techniques will actually carry through if it's non-uniform. Some bins are more likely to get the balls, and I'll try and discuss that a little bit. Okay, so if I want all the bins to have roughly the same value, roughly the same frequency, I want them all, they should all be close to the expected value, right? So I want them to be close to the expected value. Right, and so, I'm going to look at 2 ways of measuring how close they are to the expected value. Okay, so we're going to call the count estimate, CK, is going to be the max of J in the set N of F of J minus K over N. Okay, so this is the maximum difference of any bin from the expected value in the frequency count. So if some bin has 20 balls in it when it should really have 3, then this, and that's the worst case, and this will be 17. Okay. The other way of doing this, I'll call P of K, and this, because it will look more like this is more of a count, this will be more of a probability. And so, I'm going to write down another quantity here as well. So let me, this is blue. So P of J is going to be F of J over K. Okay, so this is this is going to be the empirical probability of the number of balls I expect to see in this bin. So the expected value here, the expected value of P over J, right, so what is this going to be? The expected value of P over J? 1 over n, that's right, yeah. So this is just going to have an expected value of 1 over n. This is the probability that any ball falls in the bin. And this is our measure of this probability. Okay? So P of K will be defined, it's blue, of j minus 1 over n. Okay? And so more generally, I can replace this with the expected count and this with the expected probability. But this is the empirical probability and this is the empirical frequency. Okay. So I have these two ways of measuring the error, and they look pretty similar. You know, P of k is actually C of k divided by n. So the property I want is that as the number k of my balls goes up, I want these estimates to go to 0. I want the way of measuring the evenness to get smaller and smaller. Okay, so what do you think is going to happen before we go and look at this closer? What do you think is going to happen to C of k as k gets larger? So let's say that n was equal to 100 and k was equal to 1,000, and then 10,000. Any thoughts?
Smaller, right?
It's going to get smaller.
Yeah.
So this one's actually going to get larger. Okay, so this one's going to get smaller. This one's going to get larger. Okay, so this one is going to roughly be square root n, and this one will roughly be 1 over square root n. Well, okay, so it's hard to say with n. So, yeah, so it's not, I think it's square root k. So we'll see it. So I'll write down the expression in slightly different terms, and we'll try and translate back to what they should be. But to get some good error bounds, you're roughly going to want k to be n squared, and then this one will be this one will be if this one is n squared, this one will be some constant over n. So as n is large, it'll be decreasing, and this one will be roughly a constant if it's n squared. But it's still constant. So all right. What we're going to do today is we're going to look at two expressions and show how to. What we're going to show is that the probability that pk, which is going to be this expression, is less than some value epsilon is less than delta. Okay, so this is something we want to show. This will take a while to digest what this means. Epsilon is going to be an error parameter. This will be like your percentage. You want like 1% error, then epsilon would be 0.01. So 1% error translates to epsilon equals 0.01, and delta is going to be some probability of failure. So with the randomized algorithm, you're going to have some error, and then some issues with the randomness in your algorithm. Sometimes the randomness will do really weird things in your algorithm, and you're not going to have any error bounds. And this delta says how small that probability is. So we'll spend most of the lecture looking and thinking about what these quantities mean. So this is the error. This is the probability of failure. So this is the error, and this is the probability of failure. Okay, so this is the probability that you don't have your error bound. Sorry, I got this backwards. So the probability that you have more than epsilon error is going to be less than delta. So delta is going to be something else that's small. Delta, you may say something like 0.001. So it'll turn out, in the cases we look at, it'll be a lot easier to make delta really small than epsilon small. So epsilon will be percentage error you get, it'll take more work to get this guy small, more random samples, more larger values of k, where this one you can kind of, you can amplify things, and this one you can get to go down exponentially fast. This one will go down polynomially fast. All right, so okay, so I'm going to spend some time writing a kind of a famous probabilistic bound and explaining it that will allow us to get results that look like this. So this general form of results is you would also see this in a lot of like if you're doing machine learning, is called probably approximately correct. So these are known as PAC bounds, P-A-C. So you're probably correct, this is the delta. You're approximately correct, this is the epsilon. So when you're doing randomized algorithms, these are the sort of bounds you need to get to. So when you're trying to show formal results, it'll look something like this for a randomized algorithm. There are also weaker forms of these bounds. Sometimes people say with high probability, that just means this is sufficiently small in certain ways. But so ideally, you'd want bounds that look like this if you want to formally analyze it. And so after today, I'll probably just, I may occasionally write up bounds like this for algorithms and say, you can get some bound that looks like this, and then refer back to this technique, which we'll go through in more detail now, but we won't have to deal with so much with these by when we kind of get used to the concept. Okay, so what I'm going to try and write out now is what's known as a Chernoff-Hoeffding bound. And so the form of this bound is actually going to look, so these are mathematicians from the early 1900s. I forget the dates on these things. The bound, I'll write out an easier to use form of this bound that looks like a bound from a Zuma, but that bound has more complicated setup. So this is this is a nice form of a Chernoff-Hoeffding bound. Okay. So we're going to start with a set of IID random variables. Okay. So when it's IID, that means independently and identically distributed. So that means that each of these variables are going to be independent, and they're each drawn from the same sort of distribution. For a long time, even when I was in grad school, I kept seeing this term IID, and no one would ever explain it. Okay, so it's independently, identically distributed. Do you have a question? Just okay, yeah. All right. So, and then we're going to look at a quantity, which is going to be the sum of these xi's. And so we're going to need to know two things about these random variables. One is that there's going to be some quantity delta so that the random variable is going to have, so I'm right with a simple form of this. There's a slightly more general form in the notes. Each random variable is going to be between minus delta and positive delta. This is some absolute constant. And we're going to have that the expected value of each xi is equal to 0. So you can generalize this so it's the expected value is not 0, it can be something else. And so that these bounds are not, independent around 0. They can be between 7 and 8, and the expected value could be like like 7.5, and this, and you can generalize this to go through. But this will be a little bit simpler. Okay, so now that means that the expected value of each of these is 0. The expected value of m is also going to be 0. And so now we can write down this main expression that the expected value of m, okay, the probability that the expected value is greater than some parameter alpha is going to be less than 2 times x minus alpha squared over 2r delta squared. Okay, so x here, this means so put this in the box. X of z is equivalent to e to the power z. Okay, so it's a little messy if you write all this in a power, so people will write out x. That's e, where e is the base of the natural law, like 2.71. Dot, dot, dot. Okay. So this is the result. Okay, so it means that if I have a bunch of these random variables and I sum up these random variables, yeah?
That should just be m, not expected value of m, right? The
Yeah,
expected value is
yeah.
m.
Yeah, thank you. Yeah, the absolute value of m. Yeah, great. So there are versions of this where this is only one-sided. If the expected value is not 0, then you can say the difference between m and the expected value. And if you have not these bounds, then you write some bound on the difference between these two, and you can plug this into here. Here, let me show you. So if you look at the notes, so I've got a couple forms of this theorem up here. This is the version I wrote up. There's some more general form up top here. Okay, so what's going on here? So I have these random variables, and each of them I know is in a bounded range, and I know the expected value of this. And what I'm saying is if I add them up, and I want something to be I want this to be not too far from 0. The combination of them, and I can bound that, and then I can bound that in this way. All right, so I'm going to have this expression. Yeah, I'm going to write in. So how about I show you how to use this on this problem for balls and bins. So if you look in the notes here, this was something I originally wrote up for something much more general, and there's some kind of advanced applications, some of which we'll see later in class, since there's actually a full proof of this bound. The old proofs are fairly complicated. I think I've got one of the simplest proofs of this in the write-up, if you're interested. Okay, so let's figure out how to apply this to this value over here. So what I'm going to do is I'm going to have each of these random variables xi. So I'm going to prove this for a particular, start with a particular frequency fj. So I'm just going to look at one of these frequencies, and this random variable is going to be, let's start with random variable y, is going to be 1 if si is equal to j, and and 0 otherwise. Okay? So, so what do I know about this random variable? Well, its expected value is going to be, the expected value of this is going to be 1 over n. And I know it's between 1 and 0. Now that's not quite the properties I have here, so I need to transform this random variable. So that's why I use y, so now we can use x as the proper thing. So xi is, I'm going to write as yi, and I'm going to do, let's see, yi over, let's see, minus 1 over n over n. See if this is the right way to do this. So if I do yi minus 1 over n, then the expected value should be 0. Yeah?
Shouldn't be the parameter j should be represented somewhere in the y also? I mean, how can you write yi in terms of j?
Yeah, good. Alright, so it should be j in there. So I'm going to introduce another theorem that will use to get rid of the j. Right, so these bounds don't have anything to do with j, they take the maximum over j. So we'll need to come back and figure out how to take the maximum over. And this actually relates to these problems with multiple testing and lots of other things. So we'll come back and look at that. Okay, so now if I did this right, the expected value of xi should be equal to 0. And let's see, and actually let's just let's skip this one over. Okay, so it's